Hello and welcome to this workshop on forces. My name is Matthew Woods. I'm Assistant Director of the Academic Support Center here at the College of St. Rose. And this is a presentation mostly geared towards the students in Physics 190. Everything you'll need for this presentation will be in the student guide that you'll see the link for in the YouTube description when the student guide's up on the website. I ask that you please just print that out and follow it as we go through this presentation. Also, this is going to be a two-part workshop, just because it is a kind of a long presentation. There's a lot in here. So I'll let you know when it splits. It's going to be the same presentation, same student guide. I'm just going to break into at least two videos, probably just two. If any time during the presentation you have a question, I ask that you please send me an email. My email address will be displayed in the YouTube video description. There aren't any comments allowed in these videos, just to save space and not to distract anyone. So, like I said, my email will be there. Just send me an email, put the title of the workshop in the subject heading so I know what we're discussing, and I will do my best to answer all your questions. Now I'm going to just make sure that this is transparent. There we go. And as you can see, I'm doing this one on a smartboard just to help us draw some things in for later. So let's begin. Alright, so what are the objectives of this workshop? Well, they're right there. These are the four big things that you have to be able to do. And we're going to talk about determining forces, drawing free body diagrams, and a couple of Newton's laws in this first part. And I'll let you know what the second part's going to cover. So the first thing here obviously is to recognize weight and mass, just because, these are two terms that I feel in common everyday verbiage get flipped around a little bit. So let's talk about those real quick. Mass is just how much matter is in a substance. So if you have 6 kilograms of mass, you have 6 kilograms of mass. There's no changing that. All right. We measure it in grams, either milligrams, grams, kilograms, some sort of gram, and it doesn't depend on location. You know how people say you weigh less on the moon? Well, that's true, but you don't have different masses. Your mass stays constant. If you have, like I said, if you have 15 grams of mass, well, it's 15 grams here, 15 grams in Texas, 15 grams out in space. That doesn't change. What will change is weight, because weight is a measure of the force of gravity. And the gravity part here is the difference. All right, weight's a force, so it's measured in newtons. I'm actually going to move this down. And it depends on where you are. Gravity is different on Earth than it is on the moon, than it is on the sun, on Jupiter. Even on the planet Earth, we have spots where the gravity pulls a little bit differently. At the poles, because the Earth is kind of flat at the poles, it pulls a little bit more. And it's not a tremendous amount. I think the acceleration, if I remember correctly, goes from 9.81 to 9.89 or something like that. But it's a measurable amount more. So that's just a little bit of background of weight and mass. So what is a force? A force is a push or pull that results from an interaction between two objects and causes a change in the motion of an object. And that's the key for a force. If it can change the motion of an object, it's a force. Even if you're not moving something, you have the potential to do it, therefore it's a force. All right, we have 6 different types of forces. 5 of them we're going to be covering in between these two videos. All right, we're going to talk about applied forces, gravity, which we touched on, the normal force, friction, tension, and springs, but springs are the ones that we're not covering right now. All right, so we're going to talk about Isaac Newton. Newton was a genius, to be honest. He developed the 3 laws of motion because there were a lot of misconceptions at the time. People thought objects naturally wanted to be at rest. And they saw when an object was moving, if they didn't touch it, eventually it would stop. What Newton said was that an object at rest will remain at rest, and an object in motion will remain in motion unless something acts on it. And we know now that the force acting on something that's moving typically is gravity, or not gravity, sorry, is typically friction. That's what causes things to slow down. Now what does this first law mean? You need a force to start moving. All right, if you just look at an object, it's not going to move unless you do something to it. A force is required to stop moving. Like I said, that's usually friction. It can be an applied force, but typically it's friction. But a force is not required to continue moving. All right, and this was the revolutionary idea at the time. If something's moving and nothing else is acting on it, it's going to move forever. How do we apply the first law? Well, let's just talk about types of forces acting on something for now. Suppose you're pushing a block up a frictionless ramp. What forces are acting on the block? Well, if you're on Earth or anywhere that has a center of mass, excuse me for a second, I have to sneeze. I apologize about that. If you have something that has a center of mass, gravity has to act on it. All right, and that's your weight. Now, if you're pushing the block, that's the applied force. And then there's one more force, and this is the one that sometimes people kind of forget. If gravity's pulling down on the block, something has to be pushing back up on it to keep it from falling down. And that is what the normal force is. Think of it as the ramp holding the block up. Now, that's not exactly how it is. There's a lot of electrostatic stuff that you can talk about in higher up physics. But for now, let's just consider it as the ramp holding up the block, just so you can have a visual of it. Some things that you should consider when you're thinking about these. Is the block that you're pushing bouncing up and down? If it's not, which typically it won't be, does that mean there's an unbalanced force in the y direction? If it's not bouncing up and down, there is no unbalanced force in the y direction. That means that the normal force perfectly counteracts whatever force of gravity is acting on in the y direction. So that's just going to help you when we get to the next stuff when we start to calculate. So let's talk about the second law. How do we find a force? Well, the acceleration of an object produced by a net force is directly proportional to the net force, inversely proportional to the mass of the object. In layman's terms, basically that means the harder you push on something, the faster it's going to go, and the more something weighs, the more you have to push on it to make it go just as fast. Or I apologize, I shouldn't use the word weigh there. The more matter an object has, you have to push on it harder to get it to start moving. All right. Sometimes this is written like this. Acceleration equals net force over mass. So that's what each of these three means. I prefer it like this. F net equals ma. What is F net? F net is the sum of all the forces. All right. And it's in each direction. If you're just in one direction, whoops, you can straight add it. 5 newtons plus 5 newtons minus 3 newtons, and so on and so forth. But if you're in both directions, you have to break things into vectors. All right, we're going to do that in a minute. So here's an application of the second law. A rightward force is applied to a 6 kilogram object across a rough table at a constant velocity. It experiences a frictional force of 15 newtons. Determine the remaining forces on the book and the net force. Here's the process. Now I'm going to take this off the screen real quick, just because I've got a blank slide here, so I'm going to show you what to do. Alright, so now I'm going to get over to the smartboard here. First thing we've got to do is draw the free body diagram. That's where we draw the object and all the forces acting on it to make it easier to visualize. Now, you don't have to get real fancy. There's my object. And it's 6 kilograms. Alright, so what forces are acting on it? Well, a rightward force is being applied. So that's going like that. That's my applied force, Fa. and a frictional force is acting on it. And I know it's got to be to the left here because the applied force is pushing this to the right. Friction always counteracts the movement. Now for the other two forces. Remember, this has got a mass, therefore it's got to have weight. Weight acts from the center and pulls straight down. So there's weight. The normal force acts from the surface of the object straight up. And that's my Fn. Alright, so now that I've drawn it out, I've got to apply the x and y axis. Well, if my applied force is moving to the right, I'm going to say that that's my x direction. That's my positive x. The positive y would be 90 degrees to the left, counterclockwise. So that's going to be straight up. So it's going to just be looking like the typical coordinate axis there. Alright, use arrows to indicate the direction of each force applied. So I've already done that part. Label each arrow with number and sign. So I don't know the applied force. I know the weight is mass times acceleration due to gravity. So the mass is 6 kilograms. And acceleration due to gravity is 9.81 meters per second squared. And when I multiply that, I get 58.86 newtons. Now, if the normal force is what's acting in the positive direction, I've got to make this whole thing negative. So there's one of my forces right there. The other thing that I've got acting on this is the friction. And if I know friction is acting opposite of the x, and that's going to be, according to the problem, negative 15 newtons. All right, let's look for further information in the problem. All right, so we're on step 4. Well, it tells me a constant velocity. Constant velocity means acceleration is 0 meters per second squared. So constant velocity. Create a chart for the forces in each direction. Now I'm just going to hope that my chord here reaches far enough. Let's start with the forces in the x direction. Well, I've got the applied force, which I don't know yet, and I've got the force of friction, which is negative 15 newtons. How about the y direction? Well, I've got the normal force, which I don't know yet, so I'm going to call that one y, and I've got the weight, which is negative 58.86 newtons. Now, use the second law to sum up and solve the problem. Well, I know that in each direction I can do this. For instance, in the x direction, I can do F in the x equals mass times acceleration in the x. Well, I know F in the x is going to be x minus 15 equals max. Well, I know from up here that the acceleration is 0. If the acceleration is 0, this whole thing goes to 0. So x minus 15 equals 0. Well, this is easy. X equals 15 newtons. How about in the y direction? I'm actually going to change colors for this one. In the y direction, I have the normal force minus the weight. The normal force I don't know, And the weight I know is 58.86. And just like up here, I'm going to do mass times acceleration in the y. And again, that's going to be 0. So 0 equals y minus 58.86. So the y force, the normal force, is 58.86 newtons. Now the rest of the question is asking me for the net force. Well, that's going to be easy. If this is 58.86, oops, 0.86, 58.86 minus 58.86 gives me 0 newtons in the y. This is going to be 15 newtons. 15 minus 15 is going to give me 0 newtons in the x. Well, there's no net force. It just happens to be it's moving at a constant velocity. That constant velocity is just results in 0 acceleration. And that makes sense because, remember, if we go back up here, F equals ma, well, F equals 6 kilograms times 0 meters per second squared. And these should be net force. Equals 0 newtons. Remember, if you have a question, just send me an email. I'll do my best to get back to you in a timely manner. But you're going to try this next one on your own. So a rightward force is applied to a 5 kilogram object across a rough surface. It has an acceleration of plus 2 meters per second squared in the x direction. And the coefficient for friction for the block and surface is 0.1. Determine the remaining forces and the net force. And there's the force of friction down there. I'm actually going to move this so it's easy for you to see. There we go. So please pause the video and do the work, and unpause it to find your answers. The weight should be pretty straightforward. You're on a flat surface, so it's not broken into vectors. The weight's 49 newtons, pointed down. Now you can really make your x and y direction, whichever one, positive or negative. So that's why I'm just saying 49 newtons down. Oops. The normal force should be pretty straightforward as well. It's not bouncing up and down, and you're on a flat surface, so it's 49 newtons up. The frictional force will be 49 newtons. Well, I'm sorry, the applied force I have next. So the applied force is 14.9 newtons to the right, and the frictional force is 4.9 newtons left. The frictional force should be pretty straightforward. It's just the normal force times 0.1. And if I subtract these two, because that's the only way I've got an unbalanced force is in the x direction, I get 10 newtons right for my net force. Alright, this is going to conclude the first half of this presentation. I thank you, and I look forward to seeing you in part 2. Bye-bye.